All right, I thought we'll start off class. So we have kind of moved on from sequences. Not that you're not, I think there's still a little bit of homework left to have sequences in it, but we should certainly move forward and talk about limits in general. So when we were talking about sequences, we were finding if a sequence converged or diverged by taking the limit as n approaches infinity. But we can kind of extend that idea to really any sort of function we want to. So we can definitely take the limit as x goes to infinity of lots of various things. And the nice kind of part about this is really the same sort of rules apply, whether it's n or x. If you're taking the limit as it goes to infinity, it's the same work. Welcome, Lily. Here's the hand form. So when I'm looking at this first limit as x goes to infinity of 2x squared plus 3x plus 1, 5x squared minus 6x plus 2, just like before when we had the limit as n goes to infinity, when the powers on the top and the bottom are the same, or I should say when the highest powers are the same, when the degrees are the same, we can see that, oh yeah, I've got a highest power of 2 and a highest power of 2. This limit's going to end up equaling 2/5. And you can show more work for that, right? You can definitely divide every term by the highest power of x in the denominator. In fact, let me show that down here just to remind everybody. We totally have said, oh yeah, the limit as x goes to infinity of 2x squared plus 3x plus 1 over 5x squared minus 6x plus 2. If we divide everything by x squared, welcome, we get the limit x goes to infinity of 2 plus 3 over x plus 1 over x squared over 5 minus 6 over x plus 2 over x squared. And then all these things that are being divided by x, well, x is getting really, really big. So those are just all going to 0. And oh yeah, we get 2/5. What I'll say about this is on your first exam, your teacher might want you to show all this work. They probably will want you to show all this work, and we want to be able to say, oh yeah, it's going to be 2/5. But that said, you still get to know what you know, right? You're like, oh yeah, I can see the degree on the top and the degree on the bottom are the same. So I'm just going to get the quotient of the leading coefficient. And the same thing is true whether you're going to positive infinity or negative infinity. It wouldn't matter if x is getting infinitely large or negatively infinitely large. 3 divided by a very, very large number, whether it's positive or negative, still goes to 0. Same for 1 over a really large number, 6 over, right? All those still go to 0. So whether your limit is to infinity or minus infinity, you can still use this nice kind of idea. The same thing is true here. Here I have, now this one's written in a slightly misleading way. The degree on top and bottom are both 1. Highest power on top is 1. The highest power on the bottom is 1. And so this limit is going to be 7 divided by -4. Or as I would probably say, -7/4. And you can show the work in the exact same way. You would do the work by dividing everything by x to the highest power. In this case, x to the first. So here's the work we could have done. The limit as x goes to infinity of 7, as x goes to minus infinity, apologies, of 7x minus 1 over 3 minus 4x. We divide everything by x. We're going to get 7x over x minus 1 over x over 3 over x minus 4x over x, which is just the limit as x goes to minus infinity of 7 minus 1 over x over 3 over x minus 4. 1 over something, I'm gonna say this like 1,000 times probably. 1 over something really big or really negatively big is really small. So 1 over x goes to 0 as x goes to negative infinity. And 3 over x goes to 0 as x goes to negative infinity. So we end up getting -7/4. Let me pause for a second and ask if there's any questions. Cool. Yeah. For this one up here, we have a slightly different result because my highest power on the top is 2. My highest power on the bottom is 3. Here's what I would like you to think about when you're seeing this. The bottom is growing larger faster. When you have a fraction where the bottom is growing larger faster, the fraction is getting smaller. So this fraction is getting smaller and smaller and smaller. It's getting closer and closer to 0. the same work could be done. You could divide everything by x to the what power? To the third. We divide everything by x to the third, we can show that this is equal to 0. I think I'm going to let you do that on your own if you want to. Now, this last one here is kind of special. Here we have the numerator with the largest power of x. X to the third here, x squared there. This is the one where you do usually have to do more work. You usually can't just say the answer is going to be what everything's going to be. Here I know the top is growing faster than the bottom, so I know my fraction is getting larger. But it might be getting positively large, it might be getting negatively large. And so I really kind of have to check and see. Yeah, there's not a good way around it. I would say you should just do the normal thing. So here we're going to divide by, what are we going to divide by? X to the second or x to the third? It is the second. So the general rule for dealing with limits as x goes to infinity of rational expressions like this is to divide by the thing that's growing the fastest in the denominator. So here we're going to divide everything by x squared. I will show that work down here. So we take the limit x goes to infinity of 2x squared minus 4x cubed over 5x squared plus 2x plus 1. Dividing everything by x squared, we get 2 minus 4x over 5 plus 2 over x plus 1 over x squared. 2 divided by x, getting smaller and smaller. 1 divided by x squared, getting smaller and smaller. But 4 times x is getting larger and larger and larger, right? That's going off to infinity. So what we really have here is 2 minus something infinitely large over 5. So that's a negative infinity divided by 5, which is going to be just negative infinity. So when you have a higher power on top for an expression like this, you can either end up getting positive infinity or negative infinity. You're going to figure out what sign is happening here. There are other ways of approaching this. Some people like to just kind of circle the things with the highest powers and say, how does that compare with that? And look at that ratio. I should really have gotten the negative in there, negative 4x. Like you could say that this is similar to the limit as x goes to infinity of negative 4x cubed over 5x squared. You really don't even need the constants except for the signs. And then you can say that's going to be the limit as x goes to infinity of negative 4x over 5. And that's negative infinity. That's another way you could do this that some people like to do. I don't, that's not my preference. I don't like to do it that way at all. But if you like to, that's totally fine. Okay, so limits as x goes to infinity are usually this type of thing or one other type of thing. So we either have rational functions where you have powers of x over powers of x, or sometimes you have things that involve exponential functions like e to the x. For example, I don't have anything, make stuff up. For example, something like, sorry, I did have something I wanted to actually make sure I said. We're here somewhere. There we go. Yeah. Actually, before I say either of those things, here's what I would encourage you all to really think about when you're dealing with these. Might sneeze again. I want to look at the limit as x goes to infinity of e to the x, and the limit as x goes to infinity of e to the negative x. And also really a couple other things. So when I'm thinking about this, I'm really thinking about the graph of e to the x. And e to the x looks like this usual shape. So as we go, as x goes way out to the right, here's x going to infinity. The y values are also getting infinitely large. So as x goes to infinity, e to the x also gets infinitely large. And I actually write something different here. It's okay, we'll fill it in over here. On the other side of things, as x goes to negative infinity, my e to the x values get very, very small. So over here, the limit as x goes to minus infinity of e to the x is 0. Now, I don't always think about it this way. I don't really like to say in my head e to the negative infinity. That just feels weird. What I really would do with this, to be perfectly frank, is I would actually rewrite this as the limit as x goes to minus infinity of 1 over e to the negative x. Because then I can see that I have e to the negative infinity. Negative is positive, so this is really 1 over e to the infinity. E to the infinity is really big, so 1 over that's going to be really small. I like to think about things getting really big and then deciding if they're in the numerator or the denominator. That's usually how I approach this kind of thing. In fact, the same deal here. Instead of writing this as the limit as x goes to infinity of e to the negative x, I would rewrite this as the limit as x goes to infinity of 1 over e to the positive x. And then my denominator is getting very large, my fraction is getting very small. I think I'm missing one of them. Oh yeah. And then finally, the limit as x goes to negative infinity of e to the negative x. I don't actually have to do anything here. At least not from my own personal perspective of I like having a positive power. I have e to the negative infinity. That's just e to a really big number, and e to a really big number is still a really big number. So I like having these things in mind before I start trying to deal with other limits. But I'm going to attack some of these other limits the same way we just attacked the limits as x goes to infinity, by thinking about what's getting the biggest, the fastest. So let's look at, for example, where'd you go? Sure, something like this. The limit of x goes to infinity of, sure, that seems fun. 4e to the 3x over 2e to the 3x plus 5e to the 4x. All right. What's getting biggest the fastest? Yeah. And that's actually a good answer to my not very specific question. I'm going to be a little bit more specific and say the thing that's getting biggest the fastest is e to the 4x. Kind of like how in our previous problems, x cubed was getting biggest the fastest, or whatever thing was raised to the highest power was getting biggest the fastest. So here, e to the 4x does outpace e to the 3x. So I'm going to think about dividing everything by that. Now, maybe you just going to be like, James, it's going to be 0. I know it's going to be 0 because the bottom's going to be 0. And I agree that that's nice to see, but just hold on with me for a second, because I promise you there's a little bit more to see here. So I'm going to divide everything by the thing that's getting biggest the fastest that's in the denominator. So here we're going to get the limit as x goes to infinity of, all right, 4e to the 3x over e to the 4x over 2e to the 3x over e to the 4x plus 5e to the 4x over e to the 4x. Now we need to simplify. So, sorry, my limit's kind of traveling downwards over here. I get a 4, and then e to the 3x divided by e to the 4x, we subtract those powers, and 3x minus 4x is negative x. So we get e to the negative x. Same deal on the bottom. We get 2e to the negative x. And then over here we get e to the 4x over e to the 4x is just 1, so plus 5. And then I would probably do one more thing. I would probably write it as the limit as x goes to infinity of 4 over e to the x over 2 over e to the x plus 5. Because then I can see that that's definitely going to 0. That's definitely going to 0. So I've got 0 over 0 plus 5, which is just 0. You don't have to do this, by the way. I like doing this because it's how my brain works. But if you're perfectly comfortable with saying, oh yeah, I know e to the negative x is going to go to 0 as x goes to infinity, really, really, really okay. I'm just showing you the way that kind of makes the most sense in my head. Okay, now here's where things get a little bit weirder, I think, and of course, not quite enough room. What if I go the other direction? What if I take the limit as x goes to minus infinity of the same expression, 4e to the 3x over 2e to the 3x plus 5e to the 4x. Good question. It is a good question because literally I'm thinking myself like, I don't know what the answer to this is. I think I have, oh, no, I don't really. So let's see what happens if we just plug it in for a second. If you try, because that is actually what I should have said this whole time when we talk about limits is before you do anything else, it's usually a good idea to check and see what happens if we just let X do its thing. We don't manipulate this at all. Do we get something reasonable? The answer is going to be no here, but still let's check anyway. So if I'm getting e to the negative infinity, okay, I'm gonna violate my own rules here and just say I know that's going to 0. I'm gonna get 0 on top, and e to the negative infinity is 0, and e to the negative infinity is 0. And what's 0 divided by 0? That's not 0. It could be 0. That's not true. It could be 0. It could also be 5. It could be 7. It could be 32. It could be pi. It could be anything because it's what's called an indeterminate form. Let me show you something really dumb that might help you believe me just a little bit better. You don't need to write this down. What's 0 divided by 0? Well, I'm going to say 6. Let's check. 6 times 0 is 0. 0 minus 0. Oh, it works. I got 0 left over, right? That totally works. I mean, I know, all right, it's kind of dumb. But the point is, you could have picked anything, right? I picked 6. Maybe you want to pick 67 or 671. And no matter what number you put up there, even 0 or a negative number, this process still works. I would say works in quotations because it doesn't really. But the point really is that when you have a 0 over 0, and we're going to see a lot more of this today, you can get any possible answer because it's what's called an indeterminate form. The answer is not determined until we do more work. Here, I'm thinking about dividing by the thing that's getting the biggest, the fastest, but they're both going to 0. So I guess what I should be thinking about is the thing that gets the smallest, the slowest. I don't know. I'm going to try the other thing. I'm not going to divide by e to the 4x. I'm going to divide by e to the 3x. Let me show you. And that's because I'm pretty sure dividing by e to the 4x is going to make it not work out. So if I divide by e to the 3x, we're going to get the limit. X goes to minus infinity of 4e to the 3x over e to the 3x over 2e to the 3x over 3x plus 5e to the 4x over e to the 3x. And simplifying, the limit is x goes to minus infinity of 4 over 2 plus 5e to the 4x over e to the 3x is just 5e to the x. Or if I do prefer, 4 over 2 plus 5 over e to the negative x. Just so I can do it the way I usually do it, which is saying, oh yeah, that's 5 over a big number. That's going to go to 0. So here I'm ending up with 4 over 2 plus 0, which is just 4 over 2, which is 2. In some sense, although it's kind of weird to say it this way, the e to the 3x, if x is going to negative infinity, is the bigger thing. In fact, let me graph it for you. In fact, so I will point out a lot of there's some homework questions you all have that are like, say, graph this thing on Desmos and then find the limit that way. That's a totally fine way to do it. And we might talk about that a little bit, but I will show you also just how you would find the limits without Desmos, because it's totally possible to do. There we go. I just wanted to show you though, just so you can see it for real. If we graph e to the 3x versus e to the 4x, there's e to the 3x, okay, looking pretty big. And here's e to the 4x. And although it's really hard to see it, we zoom in a little bit, you can see that to the right, the e to the 4x is the bigger function. The blue one is taller than the red one. Whereas to the left, as we go to negative infinity, the e to the 4x is actually the smaller function. They cross at the y-intercept. So if one's bigger on the right, it's definitely going to be the smaller one on the left. So that's kind of how I knew in some sense that I should be dividing everything by e to the 3x here, because as you go to negative infinity, e to the 3x is the bigger of the two things. Kind of weird. Straighten out. That's a good question. I don't know the answer. Let's find out. So if I do the limit as x goes to negative infinity, but I'm going to do it kind of quick here. So if I divide everything by e to the 4x, I'm going to get 4 over e to the x, and then I'm going to get 2 over e to the x plus 5. I feel no, I don't think it's going to work out so well, because what I have here really is the limit as x goes to negative infinity of 2e to the negative x over, 4, apologies, 4e to the negative x over 2e to the negative x plus 5. And the problem is here, if x is going to negative infinity, e to the negative x is going to positive infinity. So what I have here is an infinity over infinity type. Now, you might be able to argue to yourself that, well, yeah, but those are the same, so it's like going to be 4 over 2. But at that point, you're making enough justifications that we should have just done it the other way. It's kind of like how I'm all over the place here. It's kind of like how in this problem here, if we divided everything by x cubed instead of by x squared, it would have been hard to tell if this was going to positive infinity or negative infinity. You got a question, Dana? Right. So for powers of x, like it's just like x squared, x cubed, whatever. Doesn't matter if it's positive infinity or negative infinity. It's still going to be just whatever has the highest power of x. But for e specifically, when you have e to a thing, the thing with the quote unquote bigger power is the bigger thing if we're going to positive infinity. But it kind of reverses roles if you go towards negative infinity. Yeah, yeah. I feel like I'm not 100% sure that, but yes, that seems like the right answer. I think you're right on. Yeah, I would say instead of dividing by the highest power of x, you're the highest power, you're divided by the smallest power of x. Because that's the thing that's still going to be the biggest. Yeah, Lila. Right, highest power of x that's in the denominator. Doesn't. Right. So very, very specifically, if you were into the limit as x approaches plus or minus infinity, doesn't matter if it's positive or negative infinity, of say like x to the 4th plus 5x cubed plus 7x over something like 3x to the 4th plus 7x squared plus 4, we would divide everything by x to the 4th. Whether or not it's positive or negative infinity. In a similar way, if you have the limit as x approaches positive or negative infinity of 2x squared plus 5x plus 1 over 4x to the 7th plus 6x squared plus 9, you would divide everything by x to the 7th. The highest power, regardless of if you're going to positive or negative infinity. And lastly, if you have the limit as x goes to positive or negative infinity, let's make it not too terrible. 2x cubed plus 5x plus 7 over 4x squared plus 6. You would divide everything by x squared. Now, a couple things to see here, just because I feel like saying them. Well, no, they're important here. Here, regardless of whether you're going plus or minus infinity, the answer is going to end up being 1/3. What about for this one down here, where the power on the bottom is higher than the power on the top? And the bottom is growing faster than the top is growing. Yeah, I see some people like, yeah, like that. Yeah, it's going to be 0 because the bottom is bigger, the fraction is getting smaller. Now, one of my students many years ago showed me this trick, which I thought was really clever, but I would never actually do it. They're like, well, James, really you have 0x to the 7th plus 2x squared plus 5x plus 1 on top. And so you can say that you're going to get 0 over 4, which is 0. I thought it was clever. I didn't come up with it. I was like, oh, that's me. You can do that. So, but if your power on top is lesser than your power on the bottom, you're going to get 0. And then here, the answer is actually going to depend on if you're going to positive or negative infinity. The answer is either going to be positive infinity or negative infinity, depending on. You have to look at it. That's also. You have to actually do the work when the power on top is higher, because it's usually not super easy just to see straight away what it's going to be. Well, but first actually do the division by x squared. And then, yeah. So I will just, sure, why not? If I did the division by x squared, I would get 2x on top plus 5 over x plus 7 over x squared over 4 plus 6 over x squared. And then all the dividing by x's go to 0. So I'm left with 2 times whatever x is doing over 4. So if x is going to infinity, I get infinity. If x is going to minus infinity, I get minus infinity. But that can change based on the signs of your coefficients and what you've got in the bottom. So you really have to kind of check every time. Hi, right? Yeah, what's up?
So for if it's x, like each part of x,
Yes.
what would happen if there was only
Give me an example, if you can't, if you don't mind, or if I can make one up if you don't. But uh-huh. Okay, so but like stuff with x's, like stuff with e is in the top, or stuff with just like let me ask you, are you referring to a specific homework problem? Because if you are, I can totally look at it. So I have it right here. Okay, well, let me take a look real quick. Are you like maybe something like, no, those are all kind of weird. Okay, so let me just make something up. You're thinking something like the limit as x goes to infinity of, so something like just e to the 2x on the bottom, and what kind of stuff on top? Like e to the x's? Okay, well, so it kind of depends. Well, actually here, interesting. You could do something like this. Let's say we had like 4 e to the 2x plus 5 e to the x plus 7. You could actually, if you have just a single thing in the bottom, you can actually just divide these things by that single thing. So here, if you really wanted to, you can write this as the limit as x goes to infinity of 4 e to the 2x over e to the 2x plus 5 e to the x over e to the 2x plus 7 over e to the 2x. And then we can simplify. Now, the reason I actually point this out is because this is a really good technique to use later on when we start taking derivatives and eventually antiderivatives in 17b. But if you have something that's divided by one term like this, it is usually in your interest to break it up into each thing divided by that one term. Because then we can simplify each of those and say, oh, I've got the limit as x goes to infinity of 4 plus 5 over e to the x plus 7 over e to the 2x. And that's going to go to 4 plus 0 plus 0, which is 4. Interesting. Yeah. I might as well ask it since I already thought of it. What if we went the other direction? Well, I would still probably do the same thing I did before. So the real answer is there's not always one answer, right? Sometimes different techniques are required to do a thing just because things look different. So a lot of this mathematical learning that we're doing kind of requires being willing to try some stuff. Sometimes you got to try a thing and it's not going to work. And then we try something else and maybe that doesn't work. We try a few things until something works. I'm going to try the same thing because I think it'll work. I don't actually 100% know. I should point out that is why occasionally you'll see me be like, oh, well, we did a thing and it didn't turn out the right way. So let's try something else because I didn't know what the answer was going to be. If I simplify this in the same way, let's just cut to right here. I've got 4 plus 5 over e to the x plus 7 over e to the 2x. So I don't love writing it like that though. Let's write it as the limit as x goes to negative infinity of 4 plus 5 times e to the negative x plus 7 times e to the negative 2x. And now I can see that I've got 5 e to the negative x is going to infinity. 7 e to the negative 2x is also going, excuse me, to infinity. So I'm getting 4 plus infinity, which is still infinity. So this is getting infinitely large. Cool. All right, we should definitely use our time wisely here. Let's go that way. So I think we've covered most of what's happening on what in assignment section 2.2. Most of that assignment is just limits as x goes to infinity. I think we should definitely move on to the other types of limits that are a little more intensive. Let's see, where do I want to start with this? Let's see, we can do that. Sure. Yeah, let's talk about that. Okay, so it's not exactly where you all are starting, but we're going to go there anyway. So let's graph something real quick here. We're going to graph the following. the following piecewise function, f of x is equal to x cubed plus 1 when x is less than 0, x plus 1 when x is greater than or equal to 0 and less than or equal to 2, and finally x squared plus 1 when x is greater than 2. I'm going to graph it here. So let's see, I have, so left of 0, I have y equal to x cubed plus 1. So I have the point 0, 1 right there. Obviously, I don't have the point 0, 1 right there. I almost have the point 0, 1. And it kind of does the usual x cubed looking thing. So it looks kind of like that. And then it would continue on, but we're done. And then between 0 and 2, my graph is equal to the line y equals x plus 1. If I plugged in 0, I'd get 0 plus 1, which is 1. Like to fill that point in that was open. And then when I plug in 2, 2 plus 1 is 3. And that's filled in as well. And then finally, if I go just to the right of 2, my graph becomes the graph of x squared plus 1. If I could plug in 2, 2 squared plus 1 would be 5. So I'm going to start with a hole at 2, 5, and then kind of just continue upwards like the parabola would. That's my graph of this piecewise function. Let's ask a couple questions. More than a couple, probably. So first and foremost, what's the limit as x approaches 2 from the right-hand side of this function? Oops, you can't see that. Sorry, apologies. So what does this really even mean? So this means, what is f of x getting close to as x gets close to 2 from the right side of 2? That's what the little superscript of a plus sign there means, is you're approaching 2 from the right side of 2, or the bigger than 2 side of 2. And then the little minus sign there means the left side of 2, the less than side. So, okay, well, let's see. As I approach 2 from the right, the function is getting closer and closer to a y value of 5. It's not ever getting there, but that's not what the limit is asking about. The limit is really concerned with closeness. As x gets really, really close, but not equal to 2. Important thing I should have said before. As x gets really close to 2 from the right, but not equal to 2 from the right, the y values are getting closer and closer and closer to 5. So this limit is equal to 5. As x approaches 2 from the right. You could plug in some values, right? Like if x was 2.00001, my y value would be 2.0001 squared, which is like just a little bit more than 4, plus 1. But yeah, that's pretty close to 5. Now, what I would actually do is just plug into there and say 2 squared plus 1. But okay. What about the limit from the left? As x approaches 2 from the left-hand side, well, now it's the same idea, except now we are coming at 2 from this side. So as I get closer and closer and closer to 2 from that side, I'm going to see that, well, my function values are getting closer and closer and closer to a y value of 3. So that's going to equal 3. Now let me back up and show you how I actually would have done it without the graph. If I wanted to find the limit as x approaches 2 from the right of f of x, here's what I would have said. I would have said, okay, well, x is bigger than 2. All right, I'm approaching 2 from the right side of 2. So which piece of the piecewise function do I get to use when x is bigger than 2? Top, middle, or bottom? The bottom, right? That's where x is bigger than 2. So I'm going to say, well, that's going to equal the limit as x approaches 2 from the right of x squared plus 1. And now here's something I will try to remember to do every time. Whenever you're finding a limit, first thing you want to try and do is just plug it in. If I plug in x equal to 2 for x, do I get a real value? 2 squared plus 1 is 5. I do. That's what it's equal to. What if I go, sorry, no, not what if. I do want to be clear though, you're not plugging in a number slightly larger than 2, you're plugging actually in 2 to get what this limit is equal to. So this limit is 5. Similarly, the limit as x approaches 2 from the left of this function. Well, if I'm left of 2, now we have to be careful. I'm not just gonna say I'm less than 2 anywhere I want to be. I am less than 2 and close to 2. So if I'm on the left side of 2, I'm in this little section here where x is between 0 and 2. I'm not over here way, way, way left of 2. I'm left of 2, but close to 2. I'm using this middle piece here. I'm saying, okay, that's equal to the limit as x approaches 2 from the left of x plus 1, which is equal to, I'm just going to plug it in, and get 2 plus 1, which is 3. So graphically, a limit can exist regardless of whether or not the point is filled in or not. We don't really care. Now, these are both one-sided limits. If I said, what's the limit as x approaches 2 of the function just in general, the double-sided limit, we would say that that limit does not exist. And the reason usually that the limit does not exist is because the left-hand side and the right-hand side are approaching different values. So this limit does not exist because the limit as x approaches 2 from the left-hand side of f of x does not equal the limit as x approaches 2 from the right-hand side of f of x. In fact, we should say more about that. If I can move this piece of paper. So the limit as x approaches a of f of x is equal to, typically we use capital L, if and only if the left hand and the right hand limit are both equal to that same value. So we say the limit as x approaches a from the left of f of x is equal to that value, and that's also equal to the limit as x approaches a from the right of f of x. I'm going to stress again, a two-sided limit, right? That's what this is over here. When you say the limit is x approaches a, this is the two-sided limit. Only exists if both of the one-sided limits are equal to the same value. And it is that value. In our previous function here, we could also look at the limit and say x approaches 0. So first, writing this down. If I want to find the limit as x approaches 0 from the right-hand side of f of x, I'm going to use the piece of the function that's just to the right of 0 or the bigger than 0 part, which is this middle part right here. That's where x is just a little bigger than 0, or actually bigger than 0. Limit as x approaches 0 of f of x is going to be a limit as x approaches 0 from the right of x plus 1. Now we can see if we look at the graph, if we come at 0 from the right-hand side like that, the y values are getting closer and closer to 1. And that's true if we plug it in as well. If I plug in 0, I get 0 plus 1. I'm sorry. Similarly, we approach 0 from the left. X approaches 0 from the left-hand side of f of x. Now we're going to use the piece of the piecewise function where we are left of 0. So that's this part. Whoops, you can't see that. That's this part right here where x is less than 0 or left of 0. So we're going to use that piece of the function, which is x cubed plus 1. We plug in 0, we get 0 cubed plus 1, which is 1. And now, since those are the same, we can say that the limit as x approaches 0 overall, double-sided limit of our function is equal to 1. Pause for a minute. Question, comment. If I know, see, Edgar, Alani, Josh, Daniel, not even close. Shireen, Andrea. Oh, it's like, it's with an M, right? No, I know, yeah, you know, I feel like I know, I can picture your name. It's got like, there's like a flower somewhere or something. What's your name? Megan, what's your last name? Honey Church. Oh, that's okay. The name seemed flower to me. Kyra, Malo, and oh, was it? What's your name back there, sir? Yeah, Caesar, Marilyn, Dana. Oh, Lila. I'm not the ones I know. Lila. I don't remember your name. Oh, that's okay. I want to know your name anyway. Tanya and cool. DJ, Tanya. I will probably not know your names next time, but I will try. Okay, so talk more about limits. Yeah. Let's look at one more of these graphing kind of ones, and then we will move on to kind of the more just process ones. So let's say we have the graph of the following. Let's use a new piece of paper. Who am I kidding? Let's graph f of x equal to, sure, we've got x plus 2 when x is less than 1, 7 when x is equal to 1, and 4 minus x squared when x is greater than 1. Oops, can't see that. Sorry about that. Please let me know if I'm off screen. Sometimes I just start writing and forget where I am. So here's our graph. So when x is less than 1, by the way, when you're graphing something piecewise like this, what I really think about is, okay, x is less than 1. My graph looks like y equals x plus 2, which is a straight line. I know that if I did plug in 1, 1 plus 2 would be 3. So I'm going to have an open hole at 3 for a second, 1 comma 3. And then I know my y-intercept would be 2. So it's going to look kind of like this. There's the left of 1 piece. When x is equal to 1, which means you're only going to get a point, right? If you just have x equal to a value, the value is going to be 7. So maybe way up here. Here's 1 comma 7. And finally, to the right of 1, I get 4 minus x squared, which is kind of like the right side of a downward opening parabola. So 4 minus x squared would start, 0, 4, and then come down this way like that. And then I would get that point there, and then it would kind of do that thing. Have a x-intercept of 2 comma 0. And this point here that is an open hole is 1 comma 3. We often like to label the holes on the graph, even though the graph isn't actually defined there. Green. When you say cancels out, I'm not sure what you mean. What I would say is we would have a hole regardless of even if this didn't match up there, like if this function, like for example, if instead of having 4 minus x squared, I had 5 minus x squared, I would have the same sort of graph with a hole at 1, 3, and then this point at 1, 7, and then I would be shifted up 1, so I'd look more like this. It would look like that instead. I'd still have a hole there and a hole there at 1 comma 4 if this piece was y equal to 5 minus x squared instead. So they don't have to match up to have a hole. Okay, so let's talk about the limits as we approach 1. So if I say, what's the limit as x approaches 1 from the left of f of x? Which piece do we need to use? The top. Let me get some thumbs. We need to use the top piece, the middle piece, or the bottom piece. I want to see some thumbs. I think we need to use the top piece. If we're approaching 1 from the left, we are less than 1. So we're going to do the limit as x approaches 1 from the left of x plus 2, which is going to be careful, that's not a negative 1. That is a number that is slightly smaller than 1. We're approaching positive 1 from the left-hand side. And that's going to be 1 plus 2, which is 3. Similarly, as we approach 1 from the right-hand side, now we're going to use the bottom piece because that's where x is larger than 1. So that's going to equal the limit as x approaches 1 from the right of 4 minus x squared. And when I plug it in, I get 4 minus 1 squared, which is still 3. So as far as this graph is concerned, as far as this function is concerned, the double-sided limit as x approaches 1 of f of x is indeed equal to 3. This limit exists. It's 3, because all we're saying, all this really says here, now again, now I'm saying this like 100 times, but it's important, is as x gets closer and closer and closer and closer, but not equal to 1, the y values get closer and closer and closer to 3. As close as you want. But we never actually need to get to 3 or get to 1. Limits don't care what actually happens at the point, they care what happens really, really close to that point. Okay. Fine. Yeah, cool. One thing. Not what I wanted. Questions? You're welcome to ask questions. I can. Yeah. Oh yeah, some of these are ones too. Okay. Yeah. Sure. So, evaluating limits without graphs. Let's say we had something like the limit x approaches 2 from the left of 5x squared plus 4x over 3x squared plus 1. Don't divide everything by x squared. We're not going to infinity. That's not the thing to do here. The thing when x is approaching a real number, like 2 or 3 or -5, is first just try plugging it in. And if you plug it in and get a real answer, you're done. So here, if I plug it in, I'm going to get 5 times 2 squared plus 4 times 2 over 3 times 2 squared plus 1. That looks pretty real to me. That's 5 times 4 plus 8 over 3 times 4 plus 1. That's 28 over 13. Great. It's a real number. So we're going to see shortly that you often have to do something else. But first things first, if you can, plug in a real number. Let's look at another example. Let's add the limit as x approaches -3 from the right of the cube root of x plus 11 plus e to the 6 plus x minus 5. Well, again, I'm just going to try and plug it in and see what happens. If I plug in -3, I'm going to get the cube root of -3 plus 11 plus e to the 6 plus -3 minus 5. And although it's not pretty, it is real. I don't have any weird square roots of negative numbers, logarithms of negative numbers, or division by 0. I might simplify this a little bit. -3 plus 11 is 8, and the cube root of 8 is 2. This is 2 plus 6 minus 3 is e to the 3rd minus 5. I might simplify this down to e to the 3rd minus 3, but there's nothing else I can really do with that, except use a calculator and get an approximation. Well, that's a real number. Now, sometimes when you do a limit like this, say like the limit as x approaches 3 from the left of x squared plus 4x minus 21 over x minus 3. If you plug in 3, let's see what happens. I get 9 plus 12 minus 21 over 3 minus 3, and that's 0 divided by 0. Which is not 0, it's not 1, it could be anything. But what you should see or hear or think when you read 0 over 0 is, I need to do more work. That is the real answer. When you see 0 over 0, you have to try something else. Usually it's going to mean do some algebra. That's like if you ever talk to any of my coworkers or myself, usually will say, you see 0 over 0, do some algebra. There's some exceptions, but doing some algebra is usually the way to go. Specifically, what I mean here is we're going to factor and cancel. So if I look at this limit, as x approaches 3 from the left of x squared plus 4x minus 21 over x minus 3, the numerator does factor. And we're going to see that we can factor out an x minus 3 times an x plus 7. I will point out, usually the thing that is making you get a 0 on top, like if I plugged in 3 and I got 0, that means x minus 3 should be a factor. If I plugged in positive or -2 and got 0, that would mean x minus -2 or x plus 2 should be a factor. It's a good thing to keep in mind when you're trying to factor this. And then I can cancel those factors. It is totally legitimate to cancel these because what we're saying here is x is just approaching 3. It's not actually equal to 3. So for example, if x was equal to say 2.99 and I plug that in, I'd have 2.99 times, oh, sorry, oops, sorry, I missed something there. I'd have 2.99 minus 3 times 2.99 plus 7 over 2.99 minus 3. And negative 0.01 divided by negative 0.01, those cancel out. I'm left with 2.99 plus 7, which is pretty close to 10. And that's exactly what's happening here. When they cancel the x minus 3 and the x minus 3, and then I have the limit as x approaches 3 from the left of x plus 7, then I can just plug it in and get 3 plus 7, which is 10. So the whole idea is you're allowed to cancel these factors that would make it 0 because they're not actually 0, because we're not actually plugging in 3. This is kind of the thing that we do a lot, is we're trying to find a limit, we get a 0 over 0, we do some algebra, we make some stuff go away, and then we plug it into the rest. Let's look at it. Oh, yeah. Your homework, unfortunately, has some weird problems I was looking at. Yeah. And some unfortunateness over here. Yeah, we should address that. Okay, fine. So, yeah, we'll get there. So here's what I'll say. As far as the algebra that we can do, the main kind of bread and butter thing I'm usually going to go with is factoring and canceling. Let me show you another example. Let's say we wanted to find the limit x approaches 1, 4x squared plus 5x minus 9 over 6x squared plus 7x minus 13. And we should check, but if we check and we plug it in, if I plug in 1, I'm going to get 4 plus 5 minus 9, which is 0, over 6 plus 7 minus 13, which is also 0. So this definitely is a 0 over 0 type. So we're going to do some algebra. Now, here's something like what I just said, which is really nice to know. If you know that plugging in 1 is making a polynomial equal to 0, that means that x minus 1 should be a factor. So if I'm trying to factor the top and the bottom, I am pretty well convinced that on the top I'm going to have an x minus 1, the bottom I'm going to have an x minus 1. I'm like 99.999. The limit is 1. I'm 100% sure that that's going to be true because, well, let's actually look. So if I have an x here, I need a 4x squared here, I have to multiply that by 4x for that to work. If I have a negative 9 there and a negative 1 there, I need a plus 9 here. Let's check to see that the middle terms work out. Negative 4x plus 9x gives me 5x. That checks out. Let's do the same thing for the bottom. All right. You all write down what you need for x there. I think you can, so you need something there times that gives you 6x squared. And something there times that gives you negative 13. Give you 20 seconds. Right. The only way to get something times x to be 6x squared is if it's a 6x. And the only way to get something times negative 1 to be negative 13 is a positive 13. And if we check, the middle term should work out. Negative 1 times 6x is negative 6x. 13 times x is positive 13x. And 13x plus negative 6x is 7x. And that works. Yeah. EJ, right?
Yes. So is it like just a given rule that whenever you plug in the value from the limit, it will be x minus that value if both polynomials on top and bottom are what was it, like they become 0?
Exactly. In fact, you're getting at a fundamental theorem of algebra, which is that for a polynomial, for some p of x, if you plug in some number like say 1, if p of 1 is equal to 0, then x minus 1 is a factor of p of x. That is a true thing. So exactly what you said. So it's actually really helpful, right? Now, I should say, and I should clarify, it is specifically for polynomials. It doesn't work if you've got square roots or fractions or other things, or really I should say, you have to do more work until you get it to be a polynomial, and then it works. But yeah, excellent observation. So then we can cancel the things that aren't helpful, that are canceling out. Oh, a couple things about notation here, right? Every time you write this, you should be writing the limit as x approaches whatever of your thing. And then it's equal to this, and then it's the limit of that of this equal to that, limit of that of this. I'm going to write the limit one more time, although people like to skip this step. If the limit as x approaches 1 of 4x plus 9 over 6x plus 13. Again, what is this really saying? It's saying, what is this function getting closer and closer to as x is getting closer and closer to 1? And then we plug in 1. We no longer write the limit because we are finding the limit when we plug in 1. So I'm going to get 4 times 1 plus 9 over 6 times 1 plus 13. And that's going to be 13 over 19. And that is what the limit is. So you don't need to write the limit anymore once you have actually substituted in the value that x is approaching. Not only you don't need to, you should not write the limit once you substitute in the x. Okay. Let me give you all one. I'm gonna have you try one. I'm a liar. I'm not gonna have you try one right now. I'm gonna move on because I want to show you all the things. So let's look at this next limit. The limit as x approaches 2 of the square root of x plus 7 minus 3 over x minus 2. I think fairly straightforwardly, a 0 over 0 type of thing. Plug in 2, you get 3 minus 3 over 2 minus 2. Yep, 0, 0. So the problem here is you can't just factor it. It's not a polynomial. I can't pull out an x minus 2 from the top. I don't see how to do that. Can't. When you have square roots, you have to do another thing, which is called multiplying by the. So we're going to multiply the top and bottom. Actually, let me write another equal sign here. Now, I should point out specifically the conjugate of the thing that has the square root. There are actually two conjugates here. The conjugate of x minus 2 is x plus 2. The conjugate of the square root of x plus 7 minus 3 is the square root of x plus 7 plus 3. The conjugate of a thing is just the same thing, but the middle sign is changed from whatever it was to the opposite of that. But only the one middle sign. We're not changing the plus in here to a minus. It's just going to be times the square root of x plus 7 plus 3 over the same thing, because you're only ever allowed to multiply by 1. So if someone says multiply by the conjugate, they don't mean x plus 2 over x plus 2. Because that's not going to help you get rid of the square root. When you multiply by the conjugate of a thing with a square root, look what happens. We get the limit as x approaches 2 of, so I'm going to FOIL out the top. You can totally skip this step if you know what happens. Square root of x plus 7 times square root of x plus 7 is the square root of x plus 7 squared. Square root of x plus 7 times 3. Negative 3 times the square root of x plus 7. And finally, negative 3 times 3. And then the denominator we get, you don't multiply for things that aren't conjugates. You're just going to leave it as x minus 2 times the square root of x plus 7 plus 3. And the reason is we're hoping that x minus 2 cancels out. We don't want to FOIL out the bottom part and make it look more confusing than it needs to be. So now I want to point out, when you multiply something by its conjugate, the middle terms cancel. That is always true. Right? More generally, a minus b times its conjugate, a plus b, is just a squared plus a times b minus b times a minus b squared. And oh yeah, the middle terms cancel, and you get a difference of squares. The first thing squared minus the second thing squared, which is exactly what we got here. The first thing squared minus the second thing squared. So then if we simplify a little bit, we have the limit as x approaches 2 of x plus 7 minus 9 over x minus 2 times the square root of x plus 7 is 3. Okay, x plus 7 minus 9 is x minus, I probably should just written x minus 2. Limit as x goes to 2 of x minus 2 over x minus 2 times the same thing one more time. There's a lot of writing when you take limits sometimes. And then we can cancel the x minus 2's. What am I left with on top now? 1, right? Because we did x minus 2 divided by x minus 2 and got 1. Some people like to skip this step and just plug in the 2 and say I get 1 over whatever. I like to write stuff out. So I get the limit as x goes to 2 of 1 over square root of x plus 7. That's 3. Then we plug in the 2. We get 1 over the square root of 2 plus 7 plus 3, which is 1 over 3 plus 3, which is 1/6. And that's our limit. So when we see a 0 over 0 type of limit and there's a square root, we usually multiply by the conjugate. Whether that square root's in the numerator or in the denominator. So for example, you all could try to do this one. Limit as x approaches -3 of x plus 3 over the square root. If I was going to do it, that's fine. The square root of, now I have to think, x plus 12. That's going to be boring, but fine. Minus 3. Try that one. Try multiplying the top and the bottom by the conjugate of which part? The top or the bottom? The bottom, right? Because it has to be the thing with the square root. So try that. Right, just like in this previous problem, when the square root was on top, right, we multiply by the conjugate of that. Yeah, it's whatever the conjugate of the square root part is. So I'd love to give you more time, but I'd also love to say like 10 more things. So I'm gonna move on. What I want to point out here is that you can totally FOIL out the conjugate parts, but the end result is always going to be that the pieces that are conjugates multiplied together, you're always going to get limit as x approaches -3, the first part squared minus the second part squared. The middle terms disappear. They cancel each other out. You don't need to actually write them if you don't want to. You can though. And then on top, we are not FOILing it out. We are just leaving it as this factor, x plus 3 times this factor, square root of x plus 12 plus 3. We simplify the bottom, we're going to get x plus 12 minus 9. Which is just equal to x plus 3. So I'm trying to save a little bit of writing here just so I can give you more examples. Then we've got limit as x approaches -3 of x plus 3 times the square root of x plus 12 plus 3 all over x plus 3. And those x plus 3's cancel. So we're just left with the limit as x approaches -3 of the square root of x plus 12 plus 3. Then we plug in the -3, and we get the square root of 9 plus 3, which is 6. So when we have a 0 over 0 type of limit, this is often the process where we either factor and cancel, multiply by a conjugate. There is one other thing, but I'm going to skip it for now because it's not showing up on your homework, and I want to get to the other sort of stuff. So come back to that. Let's look at one more example like this because I'm seeing it in the homework and I want to address it. So there's problem 12 in section, what, 2.3? Yeah, 2.3. It looks kind of like this. Limit as x approaches 0 from the right of the square root of, I'm going to make up different numbers, x squared plus 100 minus 10 over x. And I will certainly agree that this is a 0 over 0 type of limit. But I'll point out, it makes me a little suspicious because so far, even though I didn't want to say it, all these 0 over 0 type of limits that we've been dealing with have been two-sided limits. And we've just been like, yeah, it works the same from the right and the left. We didn't really even address it. We just kind of dealt with it and it's fine. But here, this problem, they are giving you a right and a left, which makes me curious. So let's still do the same thing. We multiply at the top and the bottom by the conjugate. Now, I should also mention, the homework assignment actually says to use a graphing calculator or Desmos to look at this graph and then try to evaluate the limits. I think that's a good tool or skill to have. I do recommend you actually try it for at least a couple of these problems, but sometimes you don't always have that as an option. So if I'm going to do this here, I'm going to get the limit as x approaches 0 from the right. So when I multiply the top out, I get x squared plus 100 minus 10 squared. On the bottom, I get x times all that stuff. Square root of x squared plus 100 plus 10. Cancel the hundreds. Or actually, cancel the 100 minus 100. And then I'm left with the limit as x approaches 0 from the right of x squared over x times the square root of x squared plus 100 plus 10. And then x squared over x, I can cancel an x and get the limit as x approaches 0 from the right of x over square root of x squared plus 100 plus 10. And now I think I can plug in x equal to 0, right? Because I canceled something. After we cancel something, that's usually a good opportunity to be like, okay, let's see what happens if I plug in 0. If I plug in 0, I get 0 over square root of 0 plus 100 plus 10, which is 0 over 10 plus 10. 0 divided by 20 is 0. Kind of weird. It's not that weird. It just feels weird to me because it's kind of atypical. Now, let me ask you all a question. Did it matter that I was approaching 0 from the right-hand side? Did I ever use that piece of information to help me figure out what this limit was? It didn't, which means you could write this all again and do the limit as x approaches 0 from the left, or you can be like, I'm pretty sure the limit as x approaches 0 from the left is also going to be 0. Totally fine. Okay, so yeah, we got time. We can do it. We can do it. The other type of limits you might encounter, or not might, you definitely are going to encounter on this homework assignment is limits where you have a non-zero number divided by 0. For example, the limit as x approaches 3 from the right of 3x minus 11 over x minus 3. As is typical, when I'm doing a limit, I'm going to try and plug it in. If I plug it in, I get, let's see, 9 minus 11 over 3 minus 3 is negative 2 over 0. Bummer. Here's the thought process. We are approaching 3 from the right. Let's say we picked a really, really close number to 3, like, I don't know, let's say 3.0001. Let's see what happens. Well, on top, I'm going to get 3 times 3.0001 minus 11 over 3.0001 minus 3. Okay, on top, I've got 9.0003 minus 11 over 0.0001. Okay, 9. Okay, I should have picked a different number. Oh, well, that's going to be like negative 1.9997 And I want to point out that dividing by 0.0001 is dividing by 1/1000. And so when I multiply by the reciprocal, I end up getting negative 1.9997 times 1,000, which is going to be negative 1,999.7. Or in other words, a pretty large negative number. And if I went even closer to 3, my result would even be more negative because the denominator would be even smaller. The end result is that typically when you divide by a number that's getting very, very small, you end up with, sorry, not a huge deal, but I am off by a 0. 1.0001 is 1/10,000, not 1/1000. Apologize. Sorry, I can't let that stand. So this should have been actually 19,997. Sorry, 0.0. Just, 10 times bigger, no big deal. Anyway, the point is that when you have division by a super duper small number, your fraction blows up. It either blows up to something really largely positive or something really largely negative. And the only thing we have to actually figure out is if it's positive or negative. So when you have a limit and you get a division by 0, there's actually a really easy way to deal with it. The limit is x approaches 3 from the right of 3x minus 11 over x minus 3. Top's going to negative 2. And if I have x approaching 3 from the right, which is slightly bigger than 3, a number slightly bigger than 3 minus 3 is a number that is very slightly positive, which I like to write as 0 with a positive superscript, or like 0 from the right. And now look at this. We have a negative number divided by a positive number, and a negative divided by a positive is negative. Negative, large. And in my mind, that's really kind of all the work you have to show for a limit like this. On the other side, if we approach 3 from the left-hand side of 3x minus 11 over x minus 3, the top is still getting relatively close to negative 2. But the denominator now is going to be ever so slightly negative because you have a number that is just a tiny bit smaller than 3 minus 3, which is going to be a little bit negative. And then negative divided by a negative is positive. And it's a large number. What does this mean graphically? Graphically, this means that at positive 3, I should say x equal to 3, we have a vertical asymptote. Because as we approach 3 from the right, our function gets negatively very large. So we're going down like that. And as we approach 3 from the left, our function gets positively large and we go up like this. Vertical asymptote. I will also mention here, if they say what's the limit as x approaches 3 in general, well, if the two limits are not getting close to the same thing, even if that thing is infinity, we said the limit does not exist. The limit as x approaches 3 of 3x minus 11 over x minus 3 does not exist because the right side and the left side are doing different things. If they are both positive infinity or both negative infinity, we would say that they were doing the same, and that would be the limit. In fact, let's see an example of that. We have time. So yeah, let's say we wanted to find the limit as x approaches, sure, -5 from the right of x squared plus 1 over x plus 5 squared. Okay, -5 from the right, I'm a little bit bigger than -5. What's a number bigger than -5? Sure, -4.9, right? But we're getting closer to 0, so we're actually kind of smaller in absolute value. So here, plugging in -5 to the top, I'm getting positive 25 plus 1 over on the bottom, I'm getting a number a little bit less negative. So negative 4.99 plus 5 is a slightly positive small number. So it looks like I've got 26 over 0, which is going to be going to infinity. Because it's a positive infinity, because it's a positive over a positive. On the other side of things, we're approaching negative 5 from the left, thinking like negative 5.01, more negative than negative 5. Then we're going to have still the same thing. We're still going to get a 25 plus 1 on top. But now in our parentheses, we have a very slightly negative number. The thing is, when you square something, it doesn't matter if it was positive or negative, it's going to end up being positive. So whether it's a positive number squared or a negative number squared, the denominator still ends up being positive, and we get infinity on that side as well. So here overall, we would in fact say the limit as x approaches negative 5 of x squared plus 1 over x squared plus 5. Sorry, x plus. Sorry, we would say the limit is x approaches negative 5 of x squared plus 1 over x plus 5 squared is indeed positive infinity. Graphically, what's happening here is at negative 5, there is a vertical asymptote, and on either side of it, the function is going up to infinity. So whether you approach from the right, you go up to infinity, or from the left, you go up to infinity. That's what's happening there. Whenever you have a limit where x is approaching a real number, and that limit ends up being infinity or negative infinity, that means you have a vertical asymptote at that x value. Here we have a vertical asymptote at x equals negative 5. In this previous one, we had a vertical asymptote at x equal to positive 3. Sure, let me hit you with one more example because there was one I found on your homework that I thought was particularly confusing. Where'd you go? I know where it is, right over. Yeah, I'm not a fan of this problem. Oh well, that's my problem, not your problem. So let's say we had something like the limit as x approaches 6 from the left of x. Make this a little more interesting. No, I don't want to make it more interesting. Just be not interesting. It's fine. This is problem 3 from section 2.3, in case you're curious, or a version of it. So if we do the thing that we should do, what's the thing I should do first? Plug it in. We plug it in, what do we get? So you get 36 minus 36 over 36 minus, sorry, not 30, 36 minus 12 times 6 is 72 plus 36. That's looking a lot like 0 over 0. So it is an indeterminate form. We're going to do the usual thing. We're going to see if we can factor and cancel. Take the limit as x approaches 6 from the left. So on top, I can factor out an x. I'm left with x times x minus 6. On the bottom, x squared minus 12x plus 36 factors as x minus 6 times x minus 6. So then we're going to cancel an x minus 6 here and an x minus 6 there. And now we have the limit as x approaches 6 from the left of x over x minus 6. And now if we plug in 6, we get 6 over 0. Is that 0 slightly positive or slightly negative? Some thumbs. Give me a thumbs up if you think that if that 0 is slightly positive. Give me a thumbs down if you think that 0 is slightly negative, and give me a thumb in the middle if you're not sure. All right, it is slightly negative because if we're approaching 6 from the left, that means we are a tiny bit less than 6, right? I always, honestly, when I say left, I think less. I'm like, left starts with L, left starts with L. So left means less and right means more. I can't think of a good word for it. Anyway, left means less. So if we're a little bit less than 6, then if we subtract 6, we're a little bit negative. right? 5.9 minus 6 is negative. The reason I don't actually plug it in is I don't want you to think of plugging in 5.9. You can think of it, but don't write it down because that's not really what we should be doing. So I'm just thinking, oh, it's a little bit less, 5.9, so that's a little bit negative. And then a positive over a negative is going to be negative overall. All right. And if we went from the other side, it would end up being positive infinity because we have the same result. Limit as x approaches 6 from the right. We still do the same algebra and get x over x minus 6. But then we'd have 6 over a very slightly 0, which would be positive. All right, Thursday, we will kind of talk more about this. We'll do a little bit of summarizing about how, what you do when you have a 0 over 0 versus a not 0 over 0. But I think you've kind of seen the highlights of what's important. See you on Thursday. And then the plan is next Tuesday to do a review before your midterm that's on Wednesday.